Everyone knows Einstein was a genius, but Dr. Stephen Reznek, our speaker tonight, will explain to us what he did and why it revolutionized science and the way everyone sees time and space. And this is the third lecture of a 4-part series he presented at the Concord Carlisle Adult and Continuing Education. And if the other presentations are available, and we will put in the chat ways that you could access them. Steve received a PhD in physics from MIT, and he's had faculty positions at MIT, the Technical University of Denmark, and the University of Bristol, England. And he has experience in the environmental area, being on the staff of the National Commission on Water Quality and also the Environmental Protection Agency, one of my favorites. The largest part of his professional career has been with a company that manufactures specialty materials in the form of fine particles. And I'm really looking forward to hearing what he has to say. Take it away, Steve.
Okay, let me see if I can bring up the talk. Oops.
Please feel free to make comments and ask questions in the chat. And Stephen also doesn't mind being interrupted, unless you know that he is.
Yeah, please interrupt me. I assume you can see me. I can't see myself, but this started, I was invited to go down to the Center for Advanced Studies down in New Jersey in 2005 to celebrate the centennial of Einstein's 4 papers. And my wife said, I don't want to go. And I said, well, we kind of have to go. And she said, I'll bring a book. And she found the talks very interesting, very, very interesting. So I took it as a challenge to me to see if I could present these papers as well as they did during that weekend. By the way, the first day was the 4 papers, and the second day was the biography of Einstein's life. The talk I'm about to give was the third of the 4 talks that I prepared for the Concord Carlisle Adult and Community Education. What I'm going to try to do is explain what Einstein said in those papers and why it was so much of a genius. The 2 of the papers were on special relativity. Now, how come it won't go down? Okay. What the 4 papers did was, see if it's going to work this time. They demonstrated there's a minimum size for matter. And before Einstein's paper, there was a big argument about whether or not atoms existed, particularly what size they were, and a minimum size for energy. Was there something smaller? Was energy continuous, or was there a packet of energy that is the smallest size? And those were 2 of the papers. And 2 of the papers were special relativity. And then again, 10 years later was the theory of general relativity. Okay, there have been creative minds, as you all know, probably much better than I do, in the arts, in religion, in philosophy, in social sciences, in mathematics, very creative people, and in physics. And let me start by giving you my paradigm of why physics is different than all of these. It starts with data, numbers in the real world, measurements on the real world to produce data. And then there's a model, and I'll talk a little bit about what that means. And then you apply math, you do calculations on the model, and then you match those calculations to the data. And when you match your calculations to the data, you say your theory has been quote unquote proven. And a match can mean not only that your theory is correct, but it can also be an explanation of what this model really means, or a prediction. And in particular, as we get into relativity, the idea that it makes a prediction is very important. A little bit about the history, what the 4 talks that I prepared. The first models were physical models. They were models of planets going around the sun. Prior to Copernicus and Galileo, the Earth was the center of the cosmos, and the things like the sun went around it, and they changed the model. But the early days, there were physical models. As time went on, post-Newton, for example, the models became conceptual. Newton said there was such a thing as a force. 2 objects could act on each other at a distance. The sun could pull on the Earth, and the Earth could pull back on the sun, or the Earth could pull on the moon, they pull on each other. It's a conceptual model. There's a thing called a force, and these 2 things could pull on each other, and that's the model. And that was force at a distance was a very, very radical thing at the time. Today, we accept that. Another idea was as of fields, that there are things that permeate space described by their math, gravitational fields, we'll talk about that. Another thing that developed, I'm not going to talk about, I said that matter had a minimum size, energy had a minimum size. One of the developments was statistical mechanics, and it was very important in these developments that Einstein played a big role in, that matter and energy had minimum sizes, and statistics played a very important in that. Let's talk a little bit about math. Geometry was the math that was used by Galileo and Kepler to describe where the planets are. Calculus is the math that was used on these concepts of fields, and probability was used in statistical mechanics, which I'm not going to talk about today. Okay, fields, a field is not something to grow beets in, is defined everywhere in space. Example, there's a gravitational field. Temperature, there's a temperature field. There's a temperature everywhere in space. There's a number. These 2 are just a number. They're called scalars, but just a number. They're electric and magnetic fields, and they're force fields. Vectors are things that have both a size and a direction. Velocity, not speed, but velocity. So many miles an hour east or northeast or in some direction. An electric field has a strength and it points in a given direction. Same thing for magnetic fields. So a vector is something that has a magnitude and a direction, and it's defined everywhere in space. There's a value, actually 3 values in 3-dimensional space. Geometry is the math of where things are. It's what was used to solve the problem of how the planets move. And calculus is the math of how things change. And specifically, it's how things change in space or time, or in both in space and time. And this calculus is the fundamental math that underlies the theory of special relativity. Okay, now we'll go into special relativity. What are space and time? And I'll bet that's a question that you haven't asked yourself in a little while. And I'm not going to be able to answer it, but I'm going to share a little bit of light onto it, that it's a little more complicated than you thought it was. Okay, special relativity, it's weird stuff. It's not what your common sense tells you. And it's not stuff that you can get at through thinking through in a commonsensical way. It's a way that unfortunately requires some mathematics. And to make matters worse, it deals with these electromagnetic fields. Electromagnetic fields is what light's made out of. It's what microwaves and infrared and ultraviolet and gamma rays are made out of, electromagnetic fields. Okay. So we have Maxwell's equations. When God said, let there be light, he didn't say it in ancient Latin, he didn't say it in Hebrew, he said it like this. Now, what this symbol means, change in space. And what this symbol means, change in times. E is the electric field. Remember, that's a vector. It's a vector that exists everywhere. It has a magnitude and a direction. It points in a direction and it has a size. B is the magnetic field. It has a size and points in a direction. Rho is just charge. It's 0 if there's no charge. J is current, 0 if there's no current. And in free space, these terms, rho is 0 and J is 0. There are no charges in space, in free space, and no charges in currents. And what these equations say, they say the change in the electric field, its spatial change, is related to the change in the magnetic field, its temporal change. And the spatial change in the magnetic field is related to the temporal change in the electric field. This funny little symbol means change in space. This funny little symbol means change in time. And again, these are vector fields. And the solution, when there's no charge around and there's no current around, a solution looks like this. There's electric fields, which we'll take as pointing up, and magnetic fields, which would take as pointing out. And there are waves that travels along, namely light waves or microwaves, and they have a frequency, and they all travel with speed c. And here's c, that's the speed of light. They travel not at c squared, but at c, the speed of light. And these equations, they look very much like the wave equations, the same equations you get for waves in an ocean, waves, sound waves. If you take, I don't know if you've seen the gym and you see these guys flipping ropes up and down, and the rope, and if you flip the end of a rope up and down, and a bump in the rope moves down the rope. Or if you stretch a long spring and you compress part of it and let it go, that compression moves down the spring. All those equations are wave equations, and they look almost exactly the same as these equations. And what they are is some feature, in this case, an electric field and a magnetic field, zooming along at some velocity. Okay, before we start that, our ideas of space and time. Evolution has given us a brain that is used to doing what I call classical mechanics around 20 miles an hour. You can throw a rock or shoot if it's trying to get a rabbit, you're trying to kill a rabbit. Cro-Magnon, your ancestors a long time ago, you're trying to kill a rabbit. And you can throw a rock at a rabbit or shoot an arrow at a rabbit. And you can judge, you can know, you can learn how far to lead that rabbit. And he's going maybe at fastest speed, 20 miles an hour. And you can solve that in your brain doing the classical mechanics, if you would, and solve that about 20 miles an hour. And if you're really talented, like Ted Williams or Roger Federer or one of those guys, maybe you can do it at 100 miles an hour. And you can dodge a rock thrown at you at 20 miles an hour. But you can't do it at any speeds faster than that. Your brain just can't process faster than that. And you can know that time affects distance. You know, if you wait another second, that rabbit will get 10 yards further away. But if something happens at 3:30, it happens at 3:30 for everybody. No matter how that person is running or moving, at 3:30 everywhere, it doesn't make any difference if that person is on a train or a bus or moving along. It's 3:30 for everybody. And that's the way your brain works. It's a brain that evolution gave you. Well, there's a little footnote I put on this. Let's go to this footnote. So you're out hunting rabbits, and then this wise guy from MIT comes along. He says, actually, light has a speed. That rabbit didn't swerve at 3:30, but he actually swerved at 3 nanoseconds earlier. So your Cro-Magnon hunter brain replies, thanks, smart guy. I'm sure I'm going to take you along the next time I hunt, or something like that. The point of all that is that we think as time and space as different. and that the speed of light is something that's too fast for you to worry about. So here's your Cro-Magnon brain. So what drove everybody crazy? And when I say everybody, I mean a couple of physicists, namely Einstein and okay. If life is a wave, it's going to be a wave in something. A wave in water, a wave in air, a sound wave in air. And it would be surprising if it didn't matter how fast we were going. Okay, think of a swimmer. Swimmer's in a river. You should see the swimmer's speeds be different if she is swimming upstream or downstream or across the river. Shouldn't we see different rates for the speed of light if we're moving? Now here's Earth, and Earth is going around the sun, and Earth is spinning on its axis. So we're moving, and light is moving, say from a star, and we're moving. Shouldn't, as we spin towards that star, shouldn't it change the speed of light as we go towards it, like the swimmer swimming upriver, or if we're going away from it, swimming downriver, or going around the sun? So shouldn't we see a change in the speed of light? And that's something, they actually even gave it a name. It was called luminiferous ether, and you spelled it with an A if you were German and without the A if you were English. And they went and they tried to look for it. If you measure the speed of sound in air, and the air is moving, that's a wind. The speed you measure will be different on whether you're measuring it upwind or downwind. If you holler to someone who's downwind from you, your voice gets there a little faster, particularly a lot faster if the wind's blowing fast. And if you holler to somebody upwind, it takes longer for your voice to get to him. Shouldn't that happen with light? Shouldn't, if you do this experiment, shouldn't it depend upon the time of the day or the time of the year, or how you're moving towards that star or away from that star, or whatever that the light's coming from? Maxwell's equation said light is a wave. Michelson and Morley measured the speed of light. In particular, they were trying to detect this ether. They tried to detect us moving through the ether. This is their experiment. They had a rotating mirror. The reason this mirror has 5 sides is that this is the only the only shape I could draw off the internet and get a good copy. I don't know how many sides their actual mirror had. You shine a pulse of light, you do a little pulse of light, it bounces off the mirror, it heads here a long ways to a fixed mirror, bounces off that mirror, it comes back, this thing rotates a little bit, and it bounces off that mirror. And if you get this rotation exactly right for this distance, the pulse of light goes straight on through. You know how fast this thing is spinning, you know how far it had to go, so you can measure the speed of light. The astounding result was that the speed of light is the same no matter the direction, whether you're doing east and west, which is the direction the Earth is rotating, north or south, the time of year, the time of day, it didn't make any difference. And that was a shock to the physics community. There are a couple of ways out of the problem. One, all modern physics is wrong. The Earth is the center of everything. Everything goes around the Earth. The Earth is sitting here in a fixed ether, and the sun's going around the Earth, and everything else is going around the Earth. Well, they didn't like that answer very much. The other is that the ether sticks to the Earth. There's a boundary layer of the ether around the Earth. There's a boundary layer of the ether around everything. And the old ether gets all twisted up as everything moves. They didn't like that answer very much either. Maybe there's some other ways out of the problem, but the way that they focused on Lorentz, Poincaré, and Einstein was that the very concept of space and time needed an update. Our Cro-Magnon brains that said time and space are separate, independent, and what we think of is wrong. We needed a more modern approach to the way we think about space and time, all because of this experiment that found the speed of light didn't make any difference, whether it was the time of day, the time of year, east, west, north, south. We had to change our ideas about time and space. Okay, physicists guessed that time was somehow changing with velocity. Lorentz added space. Time is no longer independent, and they both depend on velocity, the Lorentz equations. Actually, somebody named Voigt, and he wrote down these equations before Lorentz, but Lorentz is the one who published and did seminars on them. In 1887, same year as the experiment, Rose wrote down equations relating time and location as seen by a moving and stationary observer. Now, unfortunately, I've got to do some algebra. This is the moving observer's time, position, his X, Y, and Z position, and his time position T, and X and T, Y and Z are the time and position of the stationary observer. And this is how they related. This is the Lorentz, I'll call them equations one more time. The location a moving person measures depends on the time and position of the stationary location. And the time a moving person measures depends on the position and time of the stationary position. And that's revolutionary. Time and space are tied together by the velocity of the two frames of reference. Okay, and our poor inherited brain, evolutionarily invented brain, was not used to that at all. One consequence of our Cro-Magnon brain is the only way to think about this stuff is with math, with these equations. Well, there's other ways to do it, but they all involve math. I cannot stress how important and contrary it is. Time and space are not fixed. They're somehow or other mixed up with each other. The speed of light is independent of how you are moving. Remember, the speed of sound and air depends on whether the air is, the wind's blowing down. If you're trying to holler somebody downwind from you, your voice gets there faster, not with light. Even if the earth is rotating towards that person, or if your earth is rotating and moving towards a star, the speed at which that light moves between you and the star is independent of your motion. Lorentz says, therefore, time and space are not independent. And here is how they're related. And he writes down these equations. Okay, now think of a flash like a flash bulb. Where it is X, and when it occurred is T. These aren't distances, they're coordinates. Do not think of them as the length of space and time. Think of them as the coordinates. They're the coordinates of events, like a flash going off. I won't call them Lorentz equations, I'll call them the Lorentz transformation. They take you from the time and space coordinates in one system to the time and space coordinates in another system, which is moving. The transform tells you the time and position coordinates in a system moving with a velocity v. Here's the Lorentz transform again. And as I say, I'm sorry, I don't think anybody else can explain special relativity without this amount of math. Before we begin, let's look at the common sense approach. Common sense meaning Neanderthal approach. Okay, let's set V over C equal to 0. V over C, let's say that's equal to 0. Is that a good thing? Speed of light is 186,000 miles a second. That's almost 7 million times faster than Ted Williams' reaction time, 100 miles an hour. Let's assume the distance from here to Albany is 100 miles, and it'll take you an hour to drive if you speed at 100 miles an hour to go to Albany. In the meantime, if you had a mirror in Albany and a mirror here, light would go back and forth almost 7 million times. Light is pretty fast stuff. If you set V over C equal to 0, this is the transformation. The guy in the moving system sees distance as X minus VT. In other words, he sees the distance just as your distance plus the distance and the time it takes to travel. And he sees the time being the same. 3:30 is 3:30 no matter what. In this case, velocities add. He sees you moving plus or minus the velocity of the difference in the coordinate systems, and things act normally, things happen simultaneously. Anything that happens simultaneously in your coordinate system happens simultaneously in his. Very simple transforms, the ones you're used to because of your Cro-Magnon brain. Einstein, now we're finally getting to special relativity. Einstein starts with two concepts. The speed of light is the same for all observers. The Michelson-Morley experiment is universally true throughout the whole universe. Not true in where it was done in Ohio, not true in the United States, not true on the earth, not true everywhere. It is true everywhere, not just true in the United States. And he says the law of physics are the same for observers, whether or not they are moving with respect to each other. The laws of physics are the same, whether or not they're moving. Okay, what does relativity mean? First, it does not mean the two observers see the same thing. Think of a train whistle. If you're on the train, it's got a certain pitch. If you're in the station, the pitch seems higher if the train is coming towards you. It seems lower if the train is past the station going away from you. You hear different things. That's not what it says. It says the laws of physics are the same. This is a translation from Einstein's German. If a system of coordinates K is chosen so that in relation to it, physical laws hold in their simplest form, the same laws hold good in relation to any other system of coordinates K prime moving in uniform velocity relative to it. General relativity changes this uniform, but right now everything is uniform velocity. Einstein's genius is to make this statement and then to explore and believe its astounding implications. Okay, Lorentz completed his transform, combining space and time, and he developed some of the implications, namely time dilation, time stretches out, space contracts. Einstein recognized his two fundamental laws, speed of light is the same, physics laws are the same. And then he wrote his first of the general relativity papers. First, he showed that the Lorentz transform is inherent in Maxwell's equations. Maxwell's equations and Lorentz transform imply each other. He also developed implications of the Lorentz transform. His unique contribution was to use the two laws to discover some very fundamental natures, very fundamental characteristics, the nature of matter. He wrote two special relativity papers describing the implications, and in this review, I will try to identify which ones were Lorentz and which ones were Einstein. Okay. To a stationary observer, two events will have separation in time and space. To a moving observer, the two events will also have a separation in time and space. But both the separations in space, i.e. the length between the two locations, and the separation in time, the time lapse between the two different events, are going to be different. The length between two things in a stationary system is not equal to the length between two things in a moving system, and the time between the two occurrences are not equal. This is in the stationary system, this is in the moving system. And Lorentz knew that very, very clearly. Okay, think of two flashes. This is a star getting ready to get on the train, a star, a movie star, not a celestial star, a movie star getting ready on the train. Two photographers are taking her picture. She's holding her luggage, and their flashbulbs go off at the same time, halfway between her, and they arrive at the same time. What does the person on the train see? Einstein's, well, the first thing in one of his papers is simultaneous is not simultaneous. She sees the two flashbulbs simultaneously, the train going along. What does he see? Two flashes are simultaneous. Is it simultaneous on the train? Wrong answer number one, an ordinary person. He sees them and he says they look the same to me. Speed of light is such that he can't tell the difference. Wrong answer number 2, the wise guy from MIT. No, the light has a speed. Each flash has to go a different distance. One goes here, one goes here. They go a different distance. So they arrive at a time d divided by c apart. D is the distance here. C is the speed. They arrive in distance apart. It's not quite right. The term d over c changes simultaneity, and it's the gamma term, the v squared over c squared term, that changes the delay. It's this term here that changes the delay. And when this term, when the v, the velocity, gets near the speed of light c, when v squared over c squared gets closer to 1, this number gets small, 1 over this number gets very big. And now this is the gamma term. Einstein actually, I think, called it a gamma term too. And I've stuck some numbers in. Okay, if v over c is 5%, 5% of the speed of light, v is 5% or 95%, this is the value of gamma. And it gets, as you get 95%, the gamma term gets to above 3. And if you get to 98 or 99, it gets very big. So it's not, oops. The wise guy from MIT who just says it's d divided by c gets wrong as your speed gets very close to the speed of light. Okay, let's talk about this with Lorentz, space contraction and time dilation. Remember my warning, evolution did not equip our brains to think about what happens near the speed of light. We're stuck with about 20 miles an hour as opposed to 186,000 miles a second. Einstein had to rework many of the laws of physics. The 1905 papers treated the electrodynamics of moving bodies. But before we go there, let's go to the 2 famous problems. First is time dilation. The second is time dilation and space contraction. Why are they famous? Because every grad student, at least back when I was a grad student, had to do these problems. That's why they're famous. As soon as you took your first course in relativity, you had to do these problems. And the purpose was to show that this is weird stuff. Here's the first problem. You have a pair of twins, and one of the twins the sister is going to go hop in a rocket ship and go to a star, turn around and come back. One person goes out and comes back. Are they the same age after the trip? And the answer is no, the traveler is younger. If you do it correctly, there are 3 clocks. He has his clock or his watch, and she has her watch, and she hops in a rocket ship, and she goes out at some velocity, and she goes out to the star. You know how far it is to the star, you know how fast she was going. You use the Lorentz transform with a positive velocity in the transform, and you know what her clock says when she gets here. Then you don't worry about the turning around business. You have another clock, a third clock. You set that clock to what her clock says, and this clock comes running back. You know how far it is, same distance. You know how fast it's going. You use the minus V transform, and you know what this clock says when it gets back here, and you look at the clocks. And sure enough, only she is younger. So time travel is possible. She's traveled into his future. He's older. If she goes really fast and it's far away, he's a lot older. She has traveled into his future. So time travel is possible. Unfortunately, that's the only type of travel that's possible. She can travel into his future. She can't travel into his past. She can't travel in his past and then come back into his future. Science fiction writers don't like that. Too bad, science fiction writers. The only kind of is possible is she can travel into his future. Here's the second problem. Before anybody starts moving, we've got a pole vaulter with a 20-meter long pole, pretty long pole for a pole vaulter. and we got a 10-meter barn. And this guy with the pole starts running, and he's pretty fast. He runs at 0.9, 90% of the speed of light. And first, what does the person in the barn see? What he sees is the pole is contracted. And he sees a couple of events. The first thing he sees is the front of the pole comes to the rear of the barn, opens the barn door. He sees the barn get in here. Since the pole is shorter, the next event he sees is the back of the pole at the back of the barn. Now the barn's inside, the front of the pole meets the front of the barn. It starts out, the last event is the back of the pole is out of the barn. So he sees the pole entirely in the barn. What about the guy with the pole? The guy with the pole sees a spaced contracted barn. So he sees that the pole is never entirely in the barn. He sees always that the front of the pole is well beyond the barn before the back end even gets into the barn. Okay, and that's the difference between, that's what actually the two observers see. They see entirely different things. And Lorentz knew that. And again, in my day, every grad student taking their first course in relativity knew that because they had to work it out. Einstein had an advantage with all this stuff. The Swiss Technical Institute was the center for non-Euclidean geometry. Einstein was a student of Hermann Minkowski, and Minkowski took all this and expressed it in a different way, in a geometric way. No calculus, just geometry. And he actually Minkowski laid a rigorous math basis for all this relativity. Einstein didn't really like it the way Minkowski laid it out rigorously, and he resisted it for a while. But eventually he caught on that geometrically was the way to do this, rather than all these algebraic transform. What's really going on is space is shrinking, and eventually adopted and used it in general relativity. So where does Einstein start? Maxwell's theory of light. Remember, the electric field is a tensor, and magnetic field is a tensor, and it changes in space and it changes in time. Electric field, E and B can store energy, they have energy. Light is a wave that transmits energy, and the energy is in these E and B fields. Okay, first paper, light is a beam and the two observers, and they see and measure different things. The intensity of the light is different, the frequency of the light is different, and the energy is different. Okay, the first paper, the first four parts, they use and they derive and use the Lorentz transformation. Einstein shows that the Lorentz transformation is part and parcel of the, I won't even show it, of this set of equations. Next thing is he looks at adding velocities. If a train travels at 0.9 c and a person on the train walks at 0.9 c, pretty fast walker, what velocity is one on the platform thinks the person moves? And he comes to the conclusion that they don't add up to 1.8 c, they add up to something less than c. You can't go faster than the speed of light. And in the second section of the paper, he examines the electromagnetic theory and Lorentz transformations. So, okay, here's the case. Here's the guy in the rocket ship is going at u is a fraction of the speed of light. The rocket ship is going v, a fraction of the speed of light. The total velocity is not u plus v, it's u plus v divided by 1 plus u times v. Einstein works this out for the first time and comes to the conclusion that this number is never greater than 1. Here's a little table. V is equal to 1/10 of the speed of light, a half speed of light, 9/10. U is 1/10, half, 9/10. 1/10 plus 9/10 is equal to 1/10, and the overall V is 0.9, not 1. 0.9 plus 0.9 is 1.8. The resulting velocity is 0.99. 0.5 plus 0.6 is not 0.6, it's 0.57. The point is they don't add. And you can't go back and add stages to the rockets, go faster and faster, to go faster than the speed of light. It just can't go faster than the speed of light. Or transmit energy faster than the speed of light. First conclusion. Quite a shocker, actually. The first thing in section 2, Einstein uses the Lorentz transform of the Maxwell's equations in a stationary system. Look, E, which is in the equations, and the derivatives of E are defined E at X and T, and he uses the transform to look at E prime in the moving system as a function of X prime and T prime. There's a whole lot of algebra and a little bit of calculus. What's the differential with respect to X prime? If you know the differential with respect to X, a little bit of calculus and a whole bunch of what I call algebra, just sticking things in and transforming them. And that's what he does. That's what the paper is. It's just a couple of pages of that stuff. So the second thing is the Doppler effect. The Doppler effect, it can be the change in pitch of a train. It's not exactly the same for light at high velocity observer flight as if the train whistle. It's again, the difference is this so-called gamma factor. But the pitch and the frequency changes. It's the Hubble redshift for an expanding universe. But the point is the frequency changes. When you substitute the Lorentz transform for these X's, the formulas for X and X prime, you get a change in frequency, and you get it because of this gamma factor, this V over C factor, V over C squared factor. Okay, look at the space between your hand and a lamp, particularly a heat lamp. There are electric and magnetic fields, and these electric and magnetic fields are the light energy that when you put your hand out, you feel the heat. What does the moving observer see? Space changes, Lorentz contraction of space, the electric field energy density changes, and the frequency changes. We went through the Doppler effect changes. Einstein comments in his paper, he uses this word in German, I guess. Its surprising result is the change in energy density and in the frequency are the same. Remember, E equals H nu, nu changes, energy changes. He didn't speak photon. Well, actually got close to speaking photon. He and Max Planck got the Nobel Prize for this separately. But when he did these transform, he found the energy density, energy per unit volume changed, and the frequency changed in the same amount. So that was one of the conclusions in the first part of the 1905 paper. Okay, so far, Lorentz has shown the strange length contraction and time dilation. Length and time are related to each other when you're going at some fraction of 186,000 miles a second. Einstein has shown so far, he dismisses the idea of simultaneity. That actually has some very interesting implications for things like quantum mechanics. One observer sees something happen simultaneous, another one will not see it. If it's moving at some velocity, won't see it simultaneous. He derived the Lorentz transforms for Maxwell's equations. He demonstrated that you can't go faster than the speed of light. He derived the Doppler shift. He showed that energy density is proportional to frequency, E equals H nu. That's all very neat, but so what? Remember what we said. We said data, model, math, match, prediction, the difference between physics and philosophy. The data was a negative result. C, speed of light is a constant. The model was Maxwell's equations, field equations on these vectors, vector fields, and four-dimensional space-time. That time and space are somehow related through the Lorentz transforms. That's the math. The Lorentz transforms an X and Y into Maxwell's equations. Their predictions, there were lots and lots of predictions. There's no match. We'll never send a twin to a star and back and see how young she is. You can't find a pole vaulter who can run at 160,000 miles a second. You can't send WBUR out into space at 90,000 miles a second to see if its broadcasting frequency shifts down from 90.9 to 45.5. You can't do it. There's no match. So is this just a bunch of geeks and nerds amusing themselves with philosophy and math as a result of one geek experiment? Or is there something else? Is this or is this not physics? What's the big deal? That's the big deal. Okay, Michelson and Morley said C is a constant. Lorentz transform relate time and space. The transform follow Maxwell's equation. Unmeasurable predictions, time dilation and space contraction. Einstein examines light interaction with a charged particle, the electron. He knew about electrons. J.J. Thomson had discovered the electron. Last section of paper 1 and paper 2 deal with light interacting with electron. Here comes light, here comes electron. Here's a stationary observer, and here's a moving observer. The moving observer is moving with the electron. Very last part of the paper deals with the moving electron of the beam of light. In the electric field, i.e. in the electric field of the beam of light, in electric fields, electron's got a charge, electric field's going to accelerate that charge. Two different frames are the stationary one that sees the electron moving in a straight line, and the second one is moving with the electron. The electron is still. The electric and magnetic fields accelerate that electron. Einstein calculates the energy the electron gained, which is equal to the energy the fields lose. The two observations are different. That is, different amounts of energy gained by the particle, lost by the fields. But in both, energy is balanced, it's conserved. Remember his second postulate, postulate of relativity. The basic laws of nature, energy conservation, is the same whether you're moving or not. Now comes the payoff, the next paper. Remember relativity. The laws of physics are true whether or not the observers are moving relative to each other. Remember that matter can emit light. We skip this black body radiation, but you all know if you get something hot, it'll glow and emit light. It's doing that at a much lower frequency at room temperature. It's doing that at any temperature above absolute zero, but it can emit light. The paper title is, Does the Inertia of a Body Depend on its Energy Content? Einstein does one of his famous thought experiments. This is not a real experiment. This is in Einstein's mind. An electron meets two identical bursts of light, except they go in opposite directions. Here's a particle, one of them goes this way, one of them goes this way. For a moving observer, the electron is at rest. That is, he's moving with the electron, and there are two emissions of light. For the stationary observer, the electron is moving. Two views of an electron. Again, this is a thought experiment, not a real experiment. Emits two light pulses, it gives up energy to the electric field. One view is stationary, the other is movement. They see different things. The amount of energy is different to the two observers. The difference is in the kinetic energy. This one, it gives off this light, the stationary one, the guy who's moving with the electron. Two pulses of light. One light goes this way, one light goes that way, and he's still standing still. And the other one pulse of light goes this way, one pulse of light this way, and his velocity changes because he's lost energy. The two views of electrons is it loses energy and is stationary before and after. The view of the moving is it loses energy and its velocity decreases. Einstein says, if a body gives off an amount of energy L in the form of radiation, its mass has to change because you have to see the same amount of energy. He says L over c squared equals the change in mass. That's an amazing conclusion. The guy had guts. If I had done this thing, I would have thrown it in the trash basket. Well, first place, not smart enough to do it. In the second place, imagine saying its mass changes. Now, everybody knows E equals mc squared. The paper doesn't say E equals mc squared. E over c squared is equal to m. That's what the paper says. Okay. He says, go back. This one's the kinetic energy changes. This one, the kinetic energy doesn't change. It's zero before and after. It has to lose mass. Unbelievable. Just unbelievable conclusion. Einstein, I mean, it just takes your breath away. He knows how radical it is. And this is a quote from the paper. Double negative. It is not impossible that with bodies whose energy content is variable to a high degree, for example, radium salts, the theory may be put to the test. Can you imagine? Well, you know, it's just amazing. One of them, the kinetic energy changes. One of them, it's the kinetic energy zero before and after. He says the mass has to decrease. It is an unbelievable statement. And it turns out to be true. Okay, Einstein, the data, the speed of light is independent of the observer. That's the data, no numbers. The concept, relativity, the concept, the laws of nature hold for both observers. The thought experiment, light emission, a thought emission, not a real experiment. The Lorentz transform, Maxwell's equation, the results, the Doppler shift. You can't explain the speed of light. Delta E equals delta H nu, delta H delta nu, and E delta E equals delta MC squared. And this one is measurable and is measurable. The end. It's actually not the end. I cheated a little bit. Are there other tests of relativity? Yes. First, you can accelerate small things to the speed of light, things like atomic particles. You couldn't in 1909. It's done every day now on particle accelerators. And second, you can make very precise measurements at much slower velocities. GPS systems have to be corrected for relativity, for the velocity of the satellites around the Earth. And they have to be corrected for both the speed and the difference in gravity. So they have to be corrected for both general and special relativity. So I cheated when I said, okay, the end. Okay, now I can go to chat and see if anybody asks me any question.
We have
Screen
a
broadcasting.
raised hand from Kenrick.
Yes, hello, I'm Kendrick. It's a terrific talk. Thanks for doing that.
Hey,
So-
Andy, can you allow us to start our videos so that we can see each other?
Sure. Oh, yeah, I hope you do. Start your videos and
It's
Your
disabled
microphone.
right now. The video is disabled.
Oh, my
the video's
mistake.
disabled.
Yeah, I'll take care of that.
Okay, I'll start my question. So I'm trained as a photonics engineer, and I'm very familiar with this mathematics and the whole concept. And not that I understand it in depth, though, because there's so much to it. But recently, I've come across a physicist who's talked about the fact that in Einstein's paper, kind of between special relativity and general relativity, he had several papers where he talked about the change of velocity of light in a gravitational field.
Correct.
And of course, we don't frame it that way anymore because we have this idea that it's space that's changing, and so the speed stays constant. But if you think about, for instance, light coming on different sides of the planet and then bending around the planet, we think of that as an acceleration, that curvature. So I guess what I'm wondering is, I understand the story of, it's space that's bending and the light is staying constant, but it seems to me you could transform all these equations to a Euclidean space, and then, you would have an acceleration of the light, if it was going either towards or away from a gravitational field. And I guess I'm curious about your own thoughts about that. And
I ended up being a materials engineer. I'm not I view things a little bit differently.
Mhm.
Light moves in a way, oh boy. it's going from point A to point B, and it moves in ways to minimize a certain function called the action.
Mhm.
Okay, and acceleration and bending and things like that are really fairly not connected to that. And the way you translate to someone who doesn't go through the field equations, and if you think Maxwell's equations are bad, you should see the Einstein's field equations.
Mhm.
You really have to, and nobody can think in 4 dimensions. I've talked to quite good physicists, much better than I am, and they all say you can't do it, you have to do it the math. So you end up with, oh God, how do I do it? You minimize.
Well, maybe even the inability to talk about it is kind of significant in the following sense, is that this warping of space was what was needed to solve the problem and get a consistent set of equations. But it seems to me that once you have that framework and those equations, you should be able to transform them into other coordinate systems. But nobody seems to think about that or do it. And as you're kind of suggesting, because that's not been communicated or taught, nobody even knows how to think about it properly.
Oh no, they transform those coordinate systems all the time. There are 3 clean systems out there. The first one was done quite early on the, what's this guy's name? And it gave you black holes and gravitational waves and all that. It ended up with a single equation, which is not too terrible equation. And it's for a fixed non-rotating body. And then the next one involves 5 equations for a rotating body. And then the last one is applicable to the universe as a whole, and it's just terrible. And then after that year, they're all solved by computers. So they're all done. And they're all done by computers. And there's a new program called out on the internet, The Edge of something or other, and it deals with what's going on the edge of the, oh Lord, what's the edge of a black hole called?
The event horizon?
Yeah, the event horizon, what goes on there, and why entropy and all that. So they're all solvable by a big enough computer grinding away on it.
Okay. Well, yeah. Well, anyways, thanks.
And it's only if you look at the 3 spatial dimensions that things look curved and accelerating. They're minimizing the light, either a particle or an earth or a light beam is following a path which is minimizing a certain function.
Yeah. Thank you.
In 4 dimensions, not in 3 dimensions.
And a question from our.
Yes, thank you, Stephen, for that talk. It was fascinating. I try to understand something about space and time by playing this thought experiment. If you attach your frame of reference to the photon that we think is actually moving, in a sense, it's not, because the time when the photon leaves me and arrives at a star, to the photon, it's the same time. So time doesn't exist for the photon. And in fact, what we think of as the speed of the light, I'm thinking is really the speed of time, or maybe more correctly, the speed of causation.
That's
what
right.
Do you think of that?
If you went at 0.99999 times the speed of light, you'd go around the entire universe in a second. That's right. You're 100%.
But we can't.
Right.
Matter can't travel at the speed of light. But a photon is light, and it's traveling. We think of it as traveling, but the photon is everywhere at the same time from the point of view of the photon. To me, that tells me something quite remarkable about the universe and about time. It's another way of realizing how strange this really is.
Yeah, 4 dimensions are very weird. And,
All over my
And-
hand.
yeah. But now we're getting into general relativity, which is, special relativity is simple compared to general relativity.
Okay.
But as I say, if you can, you can get matter going if you got all the energy there is. They're going 0.9999999 speed of light, and then you can go around the universe in a second.
Um,
Of
I
course, your mass is now, 0.99999 of infinity, but that's all right.
I don't understand any of it enough to ask anything terribly intelligent, but I like the idea of unidirectional time travel. But don't we also see into the past? Because what we're seeing when we look through telescopes is past things. And if we had somehow developed really good telephoto telescopes that could actually see moving people, for instance, could we do that? Is that possible?
Well, we just spent $13 billion on the web, so that's a pretty good telescope. What you see is, if you look to the furthest out you can look out, is what
thought experiment. Would it be possible in some imaginary future to develop a way of traveling to the past, not physically, but by watching like a movie?
Nope.
How come?
Because Einstein says you can. I don't know.
Well, when we look out in the telescope, we're looking to other parts of the universe, and then we're seeing events that happened a long time ago. But that doesn't mean we would be able to look in our own space and see backwards in time. It's just
Right, but it would still be backwards, wouldn't it? Not on our own, but in theirs. Like find the Star Wars planet and watch that happen.
Oh, you mean like some
Way in the
maybe
past.
watch some other civilization develop
Yeah,
that's similar to ours.
yeah.
Yeah, you can
Yeah, that
watch.
could possibly be.
You can watch a civilization, and you can watch what happens to it. What you can't do is send them a message and say, "Don't do that," and change their future. You can't travel into their past.
Mhm, mhm.
You can only travel into their future.
Right. Physically travel.
Or send a message or whatever. Or send a message.
But
What if you had a mirror on that distant planet or that distant thing that was sending out light and you were seeing light from past at that distant place? If somehow a mirror had been placed there, wouldn't events from our past go up there as light waves and get reflected from the mirror, and then
If they are 13 billion, if it takes light 13 billion years to get to us from them, we send them a signal, it's going to take 13 billion years for that signal to get back to them.
There's no universal now. I mean, we conceptually think of now as something real, but the now that 13 billion light years away is not the same now.
And there's no universal simultaneity. One observer sees there's two lights going off at the same time. The other person sees them not going off at the same time. There's no simultaneity, which, by the way, is important in certain types of nuclear reactions.
Steve,
Ellery has a question in the chat. He says, would you like to speak it, Ellery? I guess not. He hasn't unmuted himself, so I will read it. It says, A, 1 Tesla superconducting solenoid magnet is in space. With electron currents, B fields extend for many meters with energy densities, etc. An explosive charge destroys the magnet. Instantly, the currents stop. Where has all its E/M energy gone to?
It radiates at the speed of light out into space.
The explosion, right?
The energy, the B field, it goes out at the speed of light into space. It radiates.
But I think the question is, when the magnet blows up, the electromagnetic fields collapse. There's no longer any new fields. It's just like a photon would continue to extend out into space.
Yeah, the fields around this magnet are the standard loops, right?
Yes.
These loops just get bigger and bigger and bigger and bigger and bigger, and they move at the speed of light out into the universe.
But when the magnet blows up, there's no longer any more fields coming out
It
of it.
already ran.
Yeah,
Mhm.
but that field, those fields then start to move.
Yeah, they're gone. I think it's amazing that, all this theory that was done and, totally against the way our brains have evolved. And yet people spent millions of dollars to build all these wonderful, the colliders, the accelerators, and trying to get particles to move close to the speed of light as fast as they could. And of course, that happened after the atomic bomb. So they had some evidence that there were, that there was more proof than just a theory. I guess the other thing would be watching the curvature of light, the gravitational curvature of light that passes.
Oh yeah, somebody asked about that. Yeah, between 1905 and he wrote the paper in 1915 and was published in 1916. You look at a room, say it's an elevator room, and there's a hole in the wall and a light coming across, and it hits the far wall. And now it starts to accelerate. Well, the point on the far wall starts to move down because the thing is accelerating, right? So light curves with acceleration. And Einstein knew that. And he actually wrote, as somebody said, he wrote papers. He got it wrong by a factor of 2, by the way, until 10 years later when he got it right.
There was an excellent TV series you might be interested in. I put a link to it on in the chat about Einstein. And the synopsis is season 1 charts how Albert Einstein, an imaginative, rebellious patent clerk who couldn't get a teaching job or a doctorate, unlocked the mysteries of the atom and the universe, based on Walter Isaacson's critically acclaimed book, Einstein, His Life and Universe. And I remember that one of the issues was about there was going to be a solar eclipse, which would allow us on Earth to measure how the light curved because of the eclipse. You could see it. And that was an experiment they were going to do to prove whether or not he was right or not.
These 4 lectures that I made for Concord Carlisle, it's concordcarlisleace.org. And you have the way to get the lectures. This is Concord Carlisle Adult and Continuing Education. They have all kinds of programs, like driver's ed and music and all kinds of things. This was in one of their sub-programs called what's it called? Something Village University. They don't charge for Village University. They do ask for a contribution. You can write them, and you have the address. You're going to put it in the chat. It's Coultier at concordcarlisle.org or something. And you can get those 4. One of them is exactly what you were saying. Well, the first one is pre-Einstein. It's how we figured out how our solar system works. The second one is about how matter and energy come in small packets and the role Einstein played in that. And the third one is the one you've just seen, and the fourth one deals a little bit with the general theory of relativity and a little bit about quantum mechanics. The interesting thing is that Einstein was so instrumental in setting the stage for quantum mechanics, and he never liked it. He fought it the whole way. He didn't like the idea. Supposedly, he said the uncertainty principle, that God doesn't roll dice. And Niels Bohr said, who are you to tell God what he was going to do?
And probably neither one of them believed in God either. Those were all philosophical metaphors. Also, it was really
but the
fascinating
point is
little
that he
his
played,
wife had a major contribution to discovering all this, such that, in fact, in some people believe that she was as much, if not more, instrumental than Einstein in the early development of these. And she gets no credit, man.
well, I don't know why some people believe that, since there is no documented history. She was a physicist. She certainly participated. The divorce settlement, she got the money from the Nobel Prize. He got the Nobel Prize, she got the money. The role she played, she obviously didn't participate in general theory of relativity. She obviously did participate to some extent, to some unknown extent, in these 4 papers.
Well, I was watching the series.
We have a raised hand from Paul Jameson.
Yeah,
Hmm?
I was wondering, Einstein came over here. Did he come over because of Hitler and things like that?
Yes, absolutely, absolutely.
So he
They
thought,
went and got him. They went and got him and brought him over and built a center. Everybody says the center at Princeton. It's actually not part of the university. It's right adjacent to the university, but it's a separate organization.
Actually, it was really hard for him to get over here. He had to jump through amazing hoops because he waited so long. And his current wife then wanted him to do it sooner, and he wouldn't. And by the time he did, he had to get through a anti-Jewish bureaucrat to allow him to even emigrate, and he essentially converted the man who did let him through, and that he said, I want you please not to just do me. And probably saved many Jewish immigrants that would have died otherwise.
Niels Bohr was flown out and almost froze to death in a British an RAF plane, and he almost froze to death. And he stole a bottle of, like a Coke bottle full of heavy water, and took it over to England.
We have
Because
a
he was in Denmark, where it wasn't until much later that the Jews had to get out.
I see another raised hand from Mara.
Yeah, I just posted a question on chat. I can just read it quickly, but the LIGO experiments detect waves in space-time caused by accelerating black holes in a death spiral. These waves are not electromagnetic. I assume they propagate at the quote speed of light. Are the equations of their propagation similar or analogous to light propagation? What about their energy?
Yes, they're wave equations. They are, if you will, they're wrinkles in space-time. The space-time actually, Again, think of it in three spaces. They, do you know what LIGO looks like? You turned off
Yes,
your sound.
they're enormously
Do you know what
long.
LIGO looks like?
What the LIGO device looks like that detects? Yeah, they have two arms at right angles.
Right,
They're miles long, and they
4 kilometers long.
yeah, and thank you. and they one of the arms shrink by an unimaginably small amount, like less than the diameter of an atom or something like that. So yeah, I've read about them, and it's fascinating that what they can detect, and the speed at which the speed at which they spiral accelerates. So you can actually hear, if it's translated into sound, you can hear that it go, and then the something unimaginable happens at some unimaginable distant location.
If you look at those equations, and this you asked, there's one equation. What's it called? Paul, what's the closed form solution? The first one, the guy that developed in World War I.
I don't know.
Schwarzschild, the Schwarzschild equation.
Oh, yes. Oh,
The
that,
Schwarzschild equation. The Schwarzschild equation has got the wave solution in it, the free space gravitational wave solution. It's a Schwarzschild equation. So it's the one that's all nice, well, clean, reasonably clean, not awfully complicated, etc. It's a 4-dimensional equation, and it's got a wave solution, etc. It's got black holes in it. It's got a divergent if the mass is great enough, etc. And it's for the simple case where there's a big mass. Well, it doesn't have to be a big mass. It's just a mass in the center of it that's not rotating. And the free space solution, where there's no mass around, is a wave. And you can match that. You can take a situation where black holes are circling each other, or even stars are circling each other, and then you have to do a solution on a computer. And far away from that, it looks like a plane wave traveling at the speed of light. But near it, it gets very complicated. What it looks like, space, 4-dimensional space, is all twisted up. Yeah, so it's actually space and time get all bent out of shape, if you will.
They're not electromagnetic fields propagating. To me, this tells me that this so-called speed of light is something fundamental about time and space, not necessarily about magnetic and electrical fields, because something else is wrinkling, as you say, or waving. And so that's to me that
there are. Once again, it is only religion where things are true. Physics, nothing is true. Okay. Then go back. You got data, you got a model, you got a math, and you got a calculation, and they match. That's what happens. And then along comes better measurements, and you got to redo it. Okay. There right now, we think our current theory is there are 4 forces. Okay, one of them is the electromagnetic force, and then there are 2 nuclear forces. Oh, I was about to do that. Einstein discovered, well, there was this big controversy. You missed lecture 2. There was this big controversy. A guy whose name is Mach, and the reason that when you go fast in the speed of sound, you're traveling at Mach 1 and Mach 2 and Mach 3 is because this guy with name was Mach, and he was a good physicist, and he didn't like what these guys were doing with statistical mechanics, and he was modeling. He said, look, matter's made up of a bunch of these little things. And Mach didn't like that at all. And he said, look, make real physical measurements, measure specific heats and speeds of sound and conductivities and blah, 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 and relate them, and forget about these dippy little models, which are based on this funny little kind of probability theory. And if you're so smart, how big are these little atoms? You know, and it got quite acrimonious. They'd have these conferences and they'd almost be screaming at each other. And along come Einstein, and Einstein says, aha, Brownian motion. This is how big an atom is. So Einstein ended the fight and said there is the smallest amount of matter. You know, there's no smaller, there's no piece of iron that's any smaller than 6 times 10 to the minus 23rd of a mole. And after that, but the problem was, and then already J.J. Thomson had said, look, it looks like the solar system. There's this thing in the middle, which is positive charge, and there's an electron spinning around it. Okay, all those little things in the middle are positive charge. How come it doesn't blow apart? There's a lot of charge in there. How come it doesn't fly apart? Okay, so Einstein, in saying they're atoms, started his own sets of problems. And off went quantum mechanics, and general relativity was Einstein. It was Einstein alone. Quantum mechanics had a whole bunch of fathers. It had to be developed by a lot of people and added to by a lot of people and understood by a lot of people. But it had its own core. So we ended up with, there are 4 forces. This is our current model. There's electrostatic forces, electromagnetic forces. There are 2 nuclear forces, one called strong and one called weak. And then there's gravitational forces. And the 3 forces, electromagnetic, strong and weak, the theories all tie together in a consistent way. And there's a thing called a standard model, which explains all the particles we know about, and it all makes sense. In this periodic table, the same way the periodic table of the atoms, ordinary quantum mechanics can explain the structure and where the electrons are and blah, blah, blah. And the same thing for this other theory does it for what's going on in the nucleus, including the electromagnetic force. But nobody has been successful in tying it into gravity. So the theory is incomplete. Gravity doesn't tie together. Now, the problem is that when you take the Schwarzschild model and you collapse, you let more and more mass build up, and star gets collapsed in a neutron, it's all one big neutron, and the neutron collapses, and you get to the singularity, the thing gets smaller than, you get that well beyond the quantum limit. You get all that mass down at teeny size. Everybody thinks that somehow or other should all come together, particularly for these singularities, what's in the middle of a black hole. But nobody's come up with a way of tying the 4th force, gravity, in with those other things. So the answer is, we don't know. Or they don't know. I'm not a physicist anymore. They don't know. I'm a material scientist these days. I'm not even a solid state physicist anymore. So you're right. There's something missing. They can't tie gravity in with the other 3 forces. They can tie the other 3 together pretty well with what's called the standard model, but they can't tie gravity in. And they've tried, believe me, they've tried.
Well, do we have any other questions?
I can try with one. The equivalence of the accelerating a person in a spacecraft and gravity always struck me as something that wasn't believable, because the force of gravity has a point in space, and the force is a vector radiate. You can think of it as a vector coming out of that point in space, where there is no point in space for the simulated gravity a person feels in an accelerating spacecraft or an elevator or whatever. So I don't see the 2 as equivalent. So that's
bingo. You got it exactly right. Locally, they're the same. Over a bigger distance, there aren't. And bingo, you got it right. And that's exactly what took Einstein 10 years to figure out. You got it exactly right. Think of it this way. In a plane sheet, plane geometry, the geometry we all learned in high school, if you're moving parallel to each other, you never get closer. But if you're in a curved space, like the surface of the earth, you move parallel to each other, you meet at the pole. It's exactly the same problem. It's exactly the same problem. And gravity is on a curved space, curved four-dimensional space, not a three-dimensional space. And it locally, if they look the same, things accelerating side by side, whether you're sitting in the chair with your bottom being pulled down by gravity or being accelerated up with the chair pushing against your bottom, inside the elevator, you can't tell the difference, but you go globally and the two things go side by side, get closer and closer. These are called tidal forces, and that's exactly the problem. And that took Einstein 10 years to figure it out. You put your finger on exactly on the problem. They aren't the same. They're the same inside the elevator room, but they ain't the same on a bigger scale.
Okay.
I see another raised hand, Jim.
Yes, maybe you should say something about the reception of relativity and quantum in different countries. For example, in the Soviet Union, there was for a long time strong ideological resistance to both relativity and quantum mechanics, based on the idea that both theories were thought to be based on a philosophical idealism, which was seen as being opposed to the dialectical materialism that was the official philosophy in the Soviet Union. And the case against relativity and quantum in the Soviet Union was based on the writings of Einstein and Bohr and Heisenberg, which some of those writings were idealist interpretations of those theories, and that caused a lot of debate within the Soviet Union. There were many physicists and philosophers in the Soviet Union who totally rejected those theories. To say this is a bourgeois idealism, and they were other scientists who did theories, like Hessen was a physicist and a historian, philosopher of science. He wrote a famous paper on Isaac Newton, and his paper on Newton, which was a historical materialist interpretation of Newton's work. But one of the ideas in it was that Newton's work, Newton himself was not a materialist. He was very much a theist, a very pious person. And so the underlying idea was, if a theory like Newton's physics could be given a materialist interpretation, as it was certainly in the Soviet Union, when the same could be said for relativity and quantum. They could be given materialist interpretations. The debate ended for very good materialist reasons, because Stalin wanted the atomic bomb, and his scientific advisors told him, you can't build an atomic bomb unless you make use of relativity and quantum mechanics.
In doing these talks, I was reminded that where religion starts is, where do we come from, and God, or whatever your version of whoever. If you're a Navajo, where you came out of the navel of Mother Earth and things like that, that somehow or other that's in us with our Cro-Magnon brain, and that somehow or other then that flips over to morality and all that sort of thing. But my personal view is our view of the universe and all that sort of thing has remarkably zero to do with morality and these other questions. But that's just my view.
You're not alone there.
No, I'm sure I'm not. By the way, it was announced in the beginning that I have a background in environment. When Nixon decided to practice détente, the first exchange in détente was in the environment. And the exchange had three pieces: air quality, water quality, and general nature and ecology. I was Mr. Air Quality, And we got to travel back and forth and meet with the Russians. That was quite an experience. Okay,
Right.
again, if you want to hear all 4 talks, you'll post how to get it. And as I say, it is part of the Concord Carlisle school system. They do have a budget. They do ask for a contribution. They don't demand it. And the way that you make the contribution is at Concord Carlisle ACE, Concord Carlisle ACE.org. Go on their website and make a contribution if you watch all 4 talks. The first talk is about the solar system, pre-Einstein. The second talk is why energy and matter come in minimal sizes. The third one is you had it, and the fourth one is a little bit about quantum mechanics and a little bit about general relativity.
Well, thank you.
Okay.
Steve. Thank you for the wonderful talk. And it'll be up in a couple of days on YouTube, and I'll certainly send you the link. And we appreciate you sharing your knowledge with us. So I'll stop the recording.